Department, I'd like to welcome everyone. I'm Scott Walpert, Department Chair, and we're all honored and pleased that so many people are joining us for this conference in honor of Bill's birthday. So happy birthday, Bill. Let me just explain one practical thing, because there's a question of why we're in this room. In fact, the math department's undergoing two renovations right now. One of them's our colloquium room. So our colloquium room's closed. This is the engineering building. And also that's the first floor of the math department's something of a mess because there's a renovation going on there also. Then with that said, I'm going to turn things over to Richard Wentworth. He's in fact our organizational guru.
Organizational guru, and I forgot to bring my cheat sheet. Let me just pull something up here. Sorry, everybody. I wanted to say something, fortunately, excellent. All right. Well, welcome everybody, and it's really terrific to be here for Bill's 60th birthday conference. And so the first speaker today is Nigel Hitchin, civilian professor of geometry at Oxford University, and he's received many recognitions and awards in the past, but most recently the 2016 Shaw Prize. And let me just read a little bit of the citation from that. They refer to quote, his far-reaching contributions to geometry, representation theory, and theoretical physics, the fundamental and elegant concepts and techniques that he has introduced have had wide impact and are of lasting importance. And I think it's especially relevant that we start the conference with Nigel's talk, because it's the symbiosis between Bill's work on the Milner-Wood inequality and surface group representations, at the same time that Nigel was introducing us to Higgs bundles almost 30 years ago, was very fruitful and continues to be a very fruitful area of research. And so without any more ado, I will introduce Nigel Hitchin, who's going to talk about generalized Teichmullер spaces.
Okay, thanks, Richard. So it's a great pleasure to be here at Bill's 60th birthday celebrations. I first got to know Bill in, I suppose it was about 1989 in Oxford when he had a sabbatical there. I mean, I knew his papers, and I liked in particular the one about symplectic property of the fundamental group of a surface, which has kind of carried on through a lot of my work in Higgs bundles. But I kind of first, my feelings about Bill were sort of increased when, so he moved to Oxford, and then a friend of ours ran a Montessori nursery, and Bill's daughter went there, Lizzie went there. And I think Bill, this was before I'd actually met him, I think he told our friend, Mariana, that he was coming here, and he was particularly interested in working with a mathematician who had some interesting ideas in Oxford. And she said, "Oh, you mean, let's just say X?" And he said, "No, I mean I mean Nigel Hitchin." So when she told that to my wife, I went up in estimation in my wife's eyes anyway. And but ever since then, I've followed what he's been doing with great interest, and we meet regularly in various conferences, including, actually, he gave a talk in my 60th birthday conference. So it's a great pleasure to speak now. So the points, this kind of theory that brings us together is this the theory of Higgs bundles. So let me just begin quite rapidly with the setting. So here, so we have a compact Riemann surface and a compact group G. We have a principal G bundle with connection. That's one piece of data. And then associated to that, we have this extra piece of data, a Higgs field, which you can think of as a one form with values in the bundle of Lie algebras, But it's more interesting to consider the 1-0 part of it, which of course defines the whole thing. So this is if you like, a section of the algebra bundle tensored with the canonical bundle. And the equations, the Higgs bundle equations, are these at the bottom. There's a coupled equation, nonlinear equation, relating the G connection, the curvature of the G connection to the Higgs field, and the Higgs field is holomorphic with respect to the complex structure determined by the connection A. So the link with surface group representations is that if you look at this different connection, if you take the Higgs field and its adjoint, or if you like, using the real structure given by the compact real form, then that connection, if you look at the consequences of those equations, that connection is actually flat, which means that a solution to the Higgs bundle equations gives you a flat connection, and you can get a solution to the Higgs bundle equations by taking a holomorphic piece of data, a stable pair of objects. And so that way there's this transformation between a piece of algebraic geometry, stable Higgs bundles, and representations of the fundamental group. Now, if you want representations into a real form of a complex Lie group, it's now well known what you do. You choose your G connection to take values in the maximal compact subgroup of GR, and you take the Higgs field to lie in the orthogonal complement when you decompose the Lie algebra into the Lie algebra of the maximal compact plus its orthogonal complement, then the Higgs field has to go in the complement there. And the standard example of this is if you take, so this is if you like, the canonical example of a Higgs bundle. You take your vector bundle, holomorphic vector bundle, to be direct sum of a square root of the canonical bundle and its dual, and you put on that a U1 connection, or let's call it an SO2 connection. So we're now thinking of SO2 as the maximal compact subgroup of SL2R, and then the Higgs field is there in that off-diagonal form. That's a canonical Higgs field because that 1 is canonically determined as a map from k to the half into k to the minus a half tensor k. And so that is in the M, and so the pair of those define a flat SL2R connection, which turns out to be the connection given by uniformizing the surface, Riemann surface, with that particular complex structure. But that's just one of something which turned up as I was looking around the time that Bill came to Oxford at analogues of that, and in particular SLNR. So there are higher versions of that. So in fact there are higher Teichmullers spaces corresponding to representations of the fundamental group into SLNR, and these are parameterized by holomorphic sections of differentials of degree 2 up to n. So the space of holomorphic sections of all these all these differentials turns out to be isomorphic to a component in the moduli space of representations of the surface group into SLNR. And so this is what I mean by a higher Teichmuller space. So that's a general picture, but when it comes down to the case of n equals 3, this is what you get. So your vector bundle is now again a sum of bundles naturally associated to the Riemann surface, and the Higgs field, the more general Higgs field, looks like this, where A2 is a quadratic differential and A3 is a cubic differential. So this it turns out that this space, the space of equivalence classes of solutions to the Higgs bundle equations with these V and this phi, that forms if you go through the procedure and get the flat connection, that gives you a component in the space of all representations into SL3R. So there are obvious questions that arise out of this. The first one is what is the possible holonomy? What happens what type of representation is this? And it turns out that these are the so-called positive hyperbolic elements. Every element of the fundamental group acts in this connected component by a positive hyperbolic transformation. But the other thing is there a geometrical structure? Is there a structure on the surface where we're looking at equivalence under diffeomorphism, or diffeomorphism connected to the identity? Is this moduli space actually not just the moduli space of representations, but is it, like ordinary Teichmuller space, is it a moduli space of some geometrical structure on the surface? And this was answered in a very positive way, in this case of n equals 3, by Bill and Choi, where they showed that, in fact, that convex real projective structures, the representations that correspond to those are closed in this connected component, and closed and open, and in fact the whole connected component had a realization as the Teichmuller space of convex real projective structures. So this is a very satisfactory result, and it demands an answer for the higher values of n. And I know that François Laborie has a type of geometry which corresponds to this. But I'm trying to find a different type of geometry, something which is more closely akin to projective structures or hyperbolic structures, which we can attach to these higher Teichmuller spaces, but not for finite n, but for n equals infinity. So my idea is that by going all the way to infinity, there should be some classical geometry which extends hyperbolic geometry, and that maybe somehow truncating to finite n is some kind of, if you like, pointization of this. So what does it mean to take n equal to infinity? Well, there's now a conventional view about what SU infinity should be. Namely, it should be the symplectic diffeomorphisms of the two-sphere, or sometimes you can take a different surface. So you take a surface with a symplectic structure, and you look at this infinite dimensional group of symplectic diffeomorphisms. Now, why should you think of this as SU infinity? Well, there are various reasons, but let's not go into that too much. But it has an analog of it's analogous to a compact Lie group in many ways. So one of them is this: that if we look at the Lie algebra of the group of symplectic diffeomorphisms, then it consists of, so the two-sphere is simply connected, so each such vector field, Hamiltonian vector field, is generated by a function modulo the constants, because the constant gives you a zero vector field. So it's the C infinity functions modulo the constants, or if you like, the functions whose integral over against the symplectic form is equal to 0. So you have all sorts of invariant polynomials now defined on this Lie algebra, and in particular, so here we take the function f, which we think of as lying in the Lie algebra of SU infinity, and then we can integrate f to the m against omega, take m equal 2, and this is a bi-invariant metric, positive definite bi-invariant metric, formally speaking, on this Lie algebra. So in that respect, this SU infinity is like a compact Lie group, and we're going to use it in the context of Higgs bundles in that role. So it's going to replace the compact group G. What about the other groups? Well, here actually the last time I was in Maryland was a long time ago, maybe 20 years ago, and I was beginning to talk about this sort of thing, but I had completely the wrong idea then. I may have the wrong idea now, but I think it's a bit more convincing. The first thing is that the complexification, we shouldn't think of this as a group now. That the work of Simon Donaldson has showed that if you try and understand the complexification of groups of symplectic diffeomorphisms, there are various objects which are like symmetric spaces, but you have to think in terms of Kähler potentials, and it's not an actual group. But there are roles, especially within Donaldson's work on the Kähler-Einstein equations, there are roles for some formal object which is like a complexification. But let's leave that aside for the moment. What about the other real form? Instead of SU infinity, what about SL infinity R, and what about SO infinity? Because if I want to produce an analog of these higher Teichmuller spaces, then remember I was looking at representations into SLNR, and that required a Higgs bundle where the connection was in SON. So I need to understand what SL infinity and SO infinity are. So what about SO infinity? So here's my definition of SO infinity. I take the reflection in the two-sphere about an equator, x3 equals 0, and I look at the symplectic diffeomorphisms that commute with that involution. So if I look at SO3 inside this group, then I'm looking at the fixed point of this is SO2. So this is a higher dimensional version of, if you like, SO2 sitting inside, well, SO3 thought of in some form as SU2. So what this means that the Lie algebra of SO infinity consists of the odd functions on S2 relative to this reflection, and the M, the orthogonal complement, consists of the even functions. Now what about SL infinity R? So now I'm going to take a different symplectic manifold. I'm going to take a cylinder, but let's think of it as it's easier to think of it as the cotangent bundle of the circle with its canonical symplectic form. And now I want to look at the involution, which is a reflection about the zero section of this. And I want to think of SL infinity R as the Hamiltonian diffeomorphisms of this cylinder. So in this case, the two manifold is not simply connected, so I have to. So symplectic is they're not all Hamiltonian, but it's a minor issue. And then, okay, now here is where the analogy becomes rather strained. Now I have to think of SO infinity inside SL infinity as the group that commutes with this reflection. Well, obviously that's not the same as the one that on the two-sphere, except if I have maybe diffeomorphisms of compact support in some neighborhood of the equator, then I might then they do become equivalent. But this is not essential. So those are my models. So now what am I going to do? I'm going to try and implement the theory of Higgs bundles, and by analogy with the SLNR case, try and see what substituting SO infinity into the Higgs bundle for the compact group in the Higgs bundle, and taking something in the complement, what it gives me. So first of all, start with an SU infinity connection. So this is the compact, if you like, the compact type. So what is a connection with group the symplectic diffeomorphisms of the two-sphere? Well, I take the associated two-sphere bundle. So I have a 4-manifold, M4, two-sphere bundle over my surface, and I want a symplectic connection on that. So I want the tangent bundle of M to have a horizontal distribution, and in such a way that the parallel translation, that when I lift a curve in the base up to this horizontal distribution, it gives me a symplectic diffeomorphism of the corresponding fibers. So one way of doing this will be to take, if possible, a symplectic form on the whole 4-manifold and look at the symplectic orthogonal of the fibers. That's one way of getting a symplectic connection. And then, secondly, I want my Higgs field. So the Higgs field is supposed to take values in the Lie algebra bundle. Well, that's the bundle consisting of, so the Lie algebra is the functions on the fiber. So the Lie algebra bundle, so one form with values in the Lie algebra bundle, that's a section on the pullback, a section of the pullback of the cotangent bundle of sigma on this, on the 4 manifold. So it varies in the fibers, meaning it takes values in the Lie algebra of the symplectic group of the fibers, and then you add on the equations. So in local coordinates, this is your Higgs field looks like this, where phi1 and phi2 are functions. So x1 and x2 are local coordinates on the base, on sigma, and phi1 and phi2 are functions, local functions on the 4 manifold. Now there's a distinguished hypersurface in this, which is where the Poisson bracket of these phi's is equal to 0. And the equations tell us that actually in the complement of this hypersurface, what you get is a hypercalometric, and it acquires a singularity on this hypersurface n. So well, we know very well that the only compact surfaces which admit hypercalometrics are K3 surfaces and tori. So it's quite clear that there can be no global hypercalometric, non-singular hypercalometric on this, but the equations say that we're looking at one which has a particular type of singularity along this hypersurface, and I'll say a little bit later what that is.
Excuse me, when you say singularity, you mean vanishes. What do you mean by singularity?
Yeah, I'll give you a local form for it in a minute. So the analog with SLNR is that we should take an SO infinity connection, which means that we have an involution. So an involution on M, which on each fiber is a reflection in some circle. So then these along this fixed point set, that's where this Poisson bracket vanishes. And so then the picture is that our 4 manifold is really the double of a manifold with boundaries, the double of 2 disk bundles. So we take a disk bundle and we take its double, basically. So now let me explain first of all what a hypercalometric is and what the local behavior is along this singularity. So a hypercalometric is determined by 3 symplectic forms. So this is in 4 dimensions. It's determined by 3 symplectic forms. We have 3 closed, non-degenerate 2 forms, which satisfy some algebraic constraints. So these are the constraints. And the folded situation means that that omega 1 goes into minus itself under this involution. Omega 2 and omega 3 are preserved. So in particular, omega 1 vanishes as a form on the fixed point set. So the fixed point set is this fold, and this is the local form. So near n, if the hypersurface n is given by a local coordinate x, a local function x being equal to 0, and the reflection is x goes to minus x, then this is how the 3 forms degenerate. So folded. So actually, there is a notion of folded symplectic geometry. And within that notion, omega 2 and omega 3 are folded. That means, so folded in symplectic geometry means that the form, the closed 2 form degenerates in a non-degenerate fashion over a hypersurface, and when you restrict it as a form to the hypersurface, it becomes of maximal rank. So these two, when x equals 0, these two are actually, they fit with the definition of folded in symplectic geometry. This one is rather different. This one, as a form, vanishes completely on x equals 0. So, but this is the structure that you get in this situation. And as for the metric, well, the metric looks like this. So this is the local behavior of the metric. So you can think of this in whatever way you like. So what can we say? So what do we do with the Higgs field? So the Higgs field is part of this data, and it defines a map from the manifold M. So this is a a section of the pullback of the cotangent bundle of sigma to M. So equivalently, it's a map from M into the total space of the cotangent bundle. And now the Higgs bundle, from this point of view, the Higgs field is really the pullback of the canonical complex 1 form on the cotangent bundle, and then the two real symplectic forms fit together to be a complex symplectic form, which is the pullback of the canonical complex symplectic form on this. So N is here a circle bundle. Okay, so if this is an injection, then this is a circle bundle inside the cotangent bundle. So this is the picture. So from the folded point of view, we have a bundle of hemispheres, if you like. But the Higgs field maps each hemisphere into some domain in the smoothly bounded domain in the cotangent bundle. So the geometry we're getting out of this is, well, one piece of geometry is, if you like, a Finsler metric. If this is convex and contains the origin, then this defines the unit sphere in a Finsler metric. This is a circle bundle, but only a diffeomorphic to a circle. It's Finsler geometry, anyway. So what can we say about existence? So all I've done now is to say, well, by following the analogy between the finite dimensional Teichmullер spaces and substituting for the compact group, this group of symplectic diffeomorphisms, we ought to find a family of folded hyperkähler metrics, and ideally it ought to be parametrized by, there ought to be a moduli space which is parametrized by quadratic differentials, cubic differentials, differentials of all degrees, some infinite dimensional moduli space. So, well, you can start. Where can we start? We can start with an example. And the example is to take this. So in this case, of course, the connection was SO2 sitting inside so SO2 sits inside SO3, which is a subgroup of the group of symplectic diffeomorphisms of the two-sphere. So this solution to the Higgs bundle equations should give us an example of this canonical example of this folded hyperkähler manifold. And it does, well, I don't want to write down too many formulas here. This is what you do. If you're looking for an S1 invariant hyperkähler metric on the cotangent bundle, then you use these coordinates. I don't want to go into this too much. Anyway, this coordinate U, which is essentially the norm squared of W, it satisfies a differential equation. So it's this rather simple differential equation. So basically you can understand circle invariant hyperkähler metrics by an equation called the Toda equation, which has this geometrical form. So we have a one parameter family of metrics on a surface where the second derivative with respect to the parameter is equal to the Gaussian curvature times G. So this is called the SU infinity Toda equation. And there's an obvious solution to this, since this is basically if I replace G by the volume form, this is the Gauss-Bonnet integrand. If I rescale by a constant, the metric G, then that stays the same. So if I take the hyperbolic metric and multiply it by a constant, depending on t, then I differentiate this twice. You see, I can get this, and then the global properties depend just on A and B. So, in fact, there are some basic choices of A and B. B is essentially the Euler characteristic, which give us a solution corresponding to the canonical model. So that's a good standard example. And all I've done is basically to realize that SO2 sits inside my SO infinity and go through the whole process, but reinterpreting all the pieces of the Higgs bundle into the properties of the hyperkähler metric. Well, this was extended when I started looking at this, I started talking to Olivier Bicard, and he came up with a very nice result that in fact there exist global deformations of this canonical solution, and that there is a special family within this family of global deformations. So these are deformations as folded hyperkähler metrics. So the special family has a holomorphic projection to sigma, which means that what we get is something sitting inside the holomorphic cotangent bundle of sigma. And it's parameterized by, well, it's the CR holomorphic functions on this unit circle bundle. So my Finsler metric is determined by this circle bundle inside the cotangent bundle. The total space of the cotangent bundle is holomorphic, so the CR holomorphic functions on this are actually parameterize these deformations. So if you look at the Fourier components of these under the action of the circle, that is at the canonical solution, which is S1 invariant, then this gives you the holomorphic differentials. So ultimately the space of holomorphic differentials of all degrees is encoded here in the CR holomorphic functions on this. So what this tells me is that there are indeed deformations. I mean, there is some kind of infinite dimensional Teichmullер space, but as it stands here, it is a Teichmuller space which is a moduli space for these hyperkähler metrics, these folded hyperkähler metrics. So it's like saying that there is a distinguished space of Higgs bundles which is parameterized by differentials of degree 2, 3, 4, 5, etc. The question is that now what global properties these deformations have, and that is going to be a very difficult thing to find out.
So
Yeah.
we fix so we start with this S2 bundle.
Yeah.
Fix that topological type, and do we also fix an involution where we want the fold to occur along, and that's
No, but the deformation theory says that the fold is the fixed point set is equivalent under a family of symplectic diffeomorphisms. Yeah. So it deforms. It's essentially a local I mean, we don't know what happens a long way out. You know, if you like, if these CR holomorphic functions get large and large, we don't really know what the properties are. But that's right. So we're the topological type that we're fixing is that, if you like, that this two-sphere bundle is the projective completion of the canonical bundle. So it's, I mean, as a two-sphere bundle, it's this projective bundle of k plus 1. So the total space of the cotangent bundle sits inside here as the canonical metric, if you like, the hyperbolic metric splits this into two hemispheres, and then we're looking at deformations of that. So this is the topological type we're looking at. There are other cases. Of course, there are other real Higgs bundles with, I mean, as we know, there are other components in the representations of the fundamental group into SL2R, which correspond to different values here, but then the singularity structure, there are other singularities other than the fold. So the question which hangs around now is, well, where is this flat SL infinity R connection? So what we've got is a family of, if you like, SU infinity Higgs bundles, which, following the analogy with the finite dimensional case, should give us some flat SL and R connection. But anyway, in this case, it should give a flat SL infinity R connection. So here is where I want to involve myself in some conjectural properties, which require some further analysis to complete. So what we've got so far is basically a hyperkähler metric on a disk bundle in the cotangent bundle, which has this fold singularity over the boundary circle bundle. So suppose I look at the complement of that disk. So that's diffeomorphic to S1 cross a half line. So the double of that would be actually diffeomorphic to the cylinder, cotangent bundle of the circle. So my conjecture is that actually there is a folded, so this is got a hypersymplectic metric on a, if you like, symplectic cylinder bundle over sigma, which is the double of this. So we look at the outside, rather than looking at the inside of the disk bundle where we have this hyperkähler metric. What I claim is that there should be a hypersymplectic metric, I'll say what that is in a minute, on the complement. And it's this which is going to link up with the flat SL infinity R connection. So the picture is not that I have, so now the picture is not that I have two hemisphere bundles. It's not that I have a hemisphere which is mapping to the disk, but I have a half cylinder which is mapping to the complement of that disk. Okay, so let me say what is a hypersymplectic metric. So this goes under a different name. So here is what a hyperkähler metric is. I've just told you. A hypersymplectic metric is very similar. It's just that there's a sign difference, right? So we have omega 2 squared, this one here. So we have, if it's genuinely hypersymplectic, then these are symplectic forms which satisfy these constraints. And it gives you a metric, now not positive definite metric, but a metric of signature 2, 2. Actually, I should have said that the signature in the folded case actually changes from 4, 0 on one side of the, on one hemisphere to 0, 4 on the other side. So the sign changes. If you look at the equation, you'll see that as x goes to minus x, then that signature changes. But now we're doing something different. We're not going from one hemisphere to another. We're going outside the disk, from inside the disk to outside the disk, and the metric should be a signature 2, 2. So this is called hypersymplectic. Oh, it's got lots of other names, but it's basically the signature 2, 2 version of hyperkähler. But it has it has special properties. So now that we've got this minus sign there, if we look at the omega 1 minus omega 2 and square that, then this is equal to 0. Okay, so omega 1 wedged with omega 2 is 0. Omega 1 squared is equal to minus omega 2 squared. So this this form here is actually okay. It's decomposable now. This is and it defines the a two-dimensional foliation. It's a decomposable 2 form in 4 dimensions, and its annihilator is a 2-dimensional foliation, and it's integrable because this is a closed form. What else? Well, if it's transverse to the fibers of this double, then it means that we have a flat connection with the diffeomorphisms of this cylinder. That's what an integrable holomorphic an integrable distribution is. That's what a foliation is. You can think of that as a flat connection with holonomy in this group. And not only that, it's actually, if we take the quotient by the foliation locally, then there's an induced symplectic structure. We've got a closed 2 form. We're factoring out by the degeneracy distribution. Then the quotient space has a symplectic form. So on the other hand, this omega 2 plus I omega 3, this was the holomorphic, the canonical holomorphic symplectic form on the cotangent bundle, and that vanishes. The fibers are Lagrangian, so omega 2 and omega 3 vanish on these fibers. So actually, on this fiber, the omega 1 minus omega 2 is equal to omega 1. So what that means is that this distribution actually gives you not just the diffeomorphism of this cylinder, but it's it's certainly a symplectic diffeomorphism, but it turns out to be Hamiltonian. So so my model of SL infinity R in terms of Hamiltonian diffeomorphisms is it fits in with this situation. So what about existence in this case? Well, so here there is a local existence theorem. So in fact, if you look at the geometry of a 3 manifold sitting inside the cotangent bundle of the surface, and such that it maps surjectively onto the surface, well, so that it's submersion onto the surface, then the local geometry is determined by this is a canonical basis. So this is work which really goes back to Cartan, but has been renewed the past 15, 20 years by Robert Bryant. So basically we have these two forms, omega 2 and omega 3. So this is the restriction of the real and the imaginary part of the holomorphic symplectic form on the cotangent bundle to this 3 manifold, this circle bundle. So they have, just from linear algebra, you know that they have a common factor, a one-form phi, which is well defined up to rescaling. But you can normalize that so that this d phi is equal to b1 wedge b2 here. And then, so this gives you a canonical basis for the cotangent bundle of this 3 manifold, and in particular there's a volume form given by this. And if you look at the dual basis, then you'll see that replacing these things by these derivatives by Lie brackets, that the x2 and x3 are actually preserve this volume form. So we have this 3 manifold with these 3 vector fields and a volume form, and 2 of these preserve it. So there's this very interesting fact that came from a result in relativity, that the what are called NARMS equations. So these are, normally speaking, NARMS equations are these ordinary differential equations for matrices V1, V2, and V3. Very symmetric. So if V1, V2, and V3 were in the Lie algebra SU2, then these will be the equations for Euler's equations for a spinning top. But if you substitute for matrices, if you substitute volume-preserving vector fields, then this gives you, if you like, the evolution of a triple of vector fields along a 3 manifold. And when you put in the time, you get a 4 manifold, and you put all this data together, and you get actually a hyperkähler metric. In fact, so in the, if you like, in Picard's global solution, so Picard gave us a solution. Okay, so if you start with this real analytic data here, that V1 at 0 should be 0, V2, so these are volume-preserving diffeomorphisms, then actually this, the Cauchy-Kovalevsky theorem tells you that there is a local solution to these equations, which gives you, in fact, a folded hyperkähler metric. So this is, I mean, so this is just locally around this circle bundle. So Picard's solution is a global one. It says that you can find global ones, but whatever data we have on our circle bundle, we can always find a local solution, if you like, on the inside of this circle, which is given by this solving these equations. So there's a corresponding set of equations which originally arose by work of Wilfried Schmidt in algebraic geometry, which has a sign difference here. And the same initial data gives you actually one of these folded hyperkähler metrics. So we do know, if you like, if we take Picard's solutions inside the disk, then we do know that a little bit outside the disk is a hypersymplectic metric, which has the but we don't know whether we can extend that to the whole of the exterior of the disk. So there's a global question to be resolved here. Now, as you might expect, the canonical example works. You just change some signs and change the values of the constants, and you find that indeed there is a nice example, and that it's been around for a long, long time. In fact, the whole class of examples like this were produced by these string theorists a long time ago. So that is a known solution. Okay, so if that's the answer, then there should be suppose for the moment that this is the answer, then there should be an analogous question about what do we mean by the holonomy of this flat connection. What possible properties of the holonomy which parallel the property of being positive hyperbolic can we ask for in this situation? So here is one suggestion. So this cylinder is a symplectic manifold. Suppose we look at the transforms of the zero section by a Hamiltonian diffeomorphism. So this is a family of everything's Lagrangian in this case, but it's good to think of it as a family of Lagrangian circles inside this symplectic manifold. Then if we have a Hamiltonian diffeomorphism, then it seems reasonable to call G hyperbolic if the zero section intersects its transform transversely in 2 points. So this is a kind of generic picture. And so here's the zero section G, here's this other one, and so this is what I would think of as being a hyperbolic Hamiltonian diffeomorphism. And why have so what happens here is that I've shaded in this part, so the complement gives us two regions, so I could integrate the symplectic form over this region or over the corresponding region the other side. If this is a Hamiltonian, this goes to this by a Hamiltonian diffeomorphism, then the integral over the other side is minus this. So if you look at these two bounded domains, then somehow there are eigenvalues, exponential plus or minus the area. And so this is a suggestion about what the property of this flat connection should be, supposing that we have this global solution. Okay, so that's a kind of side remark. Now I want to look back at the involutions, because the involutions give us I think a key to the geometry that's going on. So if I have now one of these folded hypersymplectic manifolds, then I have this involution like this. If I have the global property that I'm asking for, then I have a flat connection. The universal covering, well, there is a covering of M, which is the product of the universal covering of sigma with this cylinder. That's because it's supposed to be a flat connection, so I should trivialize on the universal covering of sigma. So the involution here gives me a map from each point here. It gives me a map into an involution on this cylinder here, an anti-symplectic involution. So here, if I'm starting with a folded symplectic manifold, then a piece of geometry that I get out of it is a map from the universal covering into the diffeomorphisms of this, which is anti-symplectic. So I want to give you two examples of this as reasons for following this line of argument. So suppose I look at not hyperbolic space for the moment, but just at R2. Then cotangent bond of the circle is the space of oriented geodesics in R2, right? The circle gives me the direction, and then the cotangent fiber gives me the different parallel geodesics. So there is a very natural anti-symplectic involution of this, whose fixed points are the geodesics going through X. So the fixed points form a circle, the geodesics through a point X. So it's this, right? So there's the point X. You just, for each geodesic, you look at a parallel one, which is the same distance on the other side of that point. And of course, any geodesic passing through that point is fixed under this involution. So analytically, this is what the involution is. So I don't know what this is called. Maybe it has a name, but it's the same thing you can do in hyperbolic space. So the oriented geodesics in the hyperbolic plane are given by, of course, the endpoints, the ordered pair of endpoints. So that's RP1 cross RP1 minus the diagonal. Symplectic form in affine coordinates is this standard form. And you have a similar involution, a similar map from the hyperbolic plane into these diffeomorphisms. So I want to generalize that, okay, and hope that this has some relevance to the property that I'm looking for. Some kind of structure on a surface which generalizes hyperbolic metric and fits into this Teichmullер space, which we know exists via Picard's results. So what I want to do is now is to show you how to construct a hypersymplectic manifold, or at least first we'll construct what's called an almost one, because there's an integrability condition, but at least to use this data to give us most of the structure of a hypersymplectic manifold. So suppose we start with a two-dimensional manifold, thinking of this as the universal covering of a compact surface, so diffeomorphic to R2, and another surface which is a symplectic surface, diffeomorphic to the cylinder. And suppose I have a map from S, my space, into the diffeomorphisms, where this map is a conjugate of a Hamiltonian diffeomorphism that by a Hamiltonian diffeomorphism for this standard reflection. So first of all, what do I get? So the fixed point set is a circle in this symplectic manifold, Lagrangian circle. So for each point of the surface X, we get each of the surface S, we get a circle sitting inside this. So there's a circle bundle, a 3-manifold here. And if I look at the derivative of this association, then what is that? That's an infinitesimal deformation of this circle. That's a section of the normal bundle. Again, thinking in terms of Lagrangian manifolds, this is given by a 1 form on that circle, but this is a Lagrangian. This is this was supposed to be transformed by a Hamiltonian diffeomorphism, so this 1 form is going to be exact. It's going to give us up to a constant a function with values in the cotangent bundle of S at that point. So it should give us, if we have a systematic way of choosing, if you like, a moment for this, or not a moment map, but choosing a function for which this is the derivative, then we'll get an embedding of N as a circle bundle in the cotangent bundle of S. So this will be this gives us a Fensler metric such that S primed is in fact the space of geodesics. So that map is going to give us this kind of data. But now I want to try and define on this product. So this is supposed to be again on the universal covering of a compact surface. I want to define an involution now on this 4-manifold, which is going to be part of the structure of a folded hypersymplectic manifold. So what have I got? I've got a symplectic form on the surface S primed. I can pull that back. And now, using the involution, I can define two forms, omega 1 and omega 2. Note that omega 1 goes into minus itself under Tor, but omega 2 goes into itself under Tor. So suppose I assume that these are symplectic. So in fact, that's not true of the map to involutions that I gave you for R2. And that's a degenerate situation. Then what have we got? We've got two symplectic forms on this 4-manifold S, which satisfy, these relations. So these are part of the relations for a hypersymplectic manifold. They are closed, and the involution satisfies the right properties. And so now let's go back to the analogy with Higgs bundles, because there we didn't just have one flat connection, but in fact, it turns out there's a whole circle, but in particular, there's a minus one here. So this is one flat GR connection, and this is another one. And in the finite dimensional situation, what you could say is that this one is gauge equivalent to that one, so that there's a map from sigma tilde into the group G, such that the difference is G inverse dG. And that this is effective, so the difference is basically the Higgs field here. So in this case, what do we get? So in this case we had omega, we had a product here, that's one flat connection, but now with this omega, we pull back omega here by the involution on here, we get another one, which is closed, so we get another flat connection. So the involution gives us this pair of flat symplectic connections. So we're approaching, by analogy, the situation that we have in the finite dimensional picture. Finally, if we take a complex structure on the surface S, then you can define, in fact, an almost complex structure on the 4-manifold. And you can define the third 2-form, omega 3, by using that structure here. And that makes omega 2 plus I omega 3 of type 2,0 with respect to this new complex structure. So what we're doing is we're using now an extra information, a complex structure on the surface S, in order to get what's looking like a hypersymplectic manifold. The only thing is that the closure of this 3-form, which is what we need to get the hypersymplectic manifold, is equivalent to an equation like this. So this is basically the differential equation for the data that I've given. This map. So you can look at it in different ways. So for the data that I've given, which was this map to the involutions, together with the complex structure on S, this gives us this hypersymplectic structure. So the question that's open now is, suppose I do have this this picture. Suppose I can prove global existence of this hypersymplectic metric in the complement of the disk bundles which are provided by B-card solutions. Is it possible that that the Teichmullер space that I'm looking at is actually a moduli space of these Finsler type structures defined by involutions? That is okay. That is not. It's not clear at all what's going to happen there, because we would need to know global properties of the metrics, convexity, and all sorts of things. There's a whole program of work to be done to try and make this work. And one of the features of it is it's unclear at the moment what the role of the complex structure is here. In the standard case, we have the flat connection that's independent of any complex structure. We choose a complex structure that gives us a description in terms of Higgs bundles. So the role of the complex structure here and its link is with the other input is not at all clear. But what I would hope is that there's some kind of deformation of hyperbolic geometry, which involves these involutions and maybe Finsler structures which are compatible with this involution, plus some global property, obviously some kind of analog of negative curvature, that this might be a type of geometry which is parameterized by this infinite dimensional Teichmullер space. Well, let me finish there by wishing Bill, I know it's now over, but a happy birthday. Okay.
Questions?
Oh, yeah.
Go ahead.
Could you sketch out how the SU ends embedded to SU intensity?
Sorry?
Could you sketch out how the the finite SUNs embed into SU?
Well, they don't. Okay, so this is the point, that they don't. What you can say is that if you look at what's called the principal SU, so inside, if you look at the irreducible, if you look at the n-dimensional irreducible representation of SU2, then if you look at this well, it's not necessarily injection, but if you look at this homomorphism, if you break up the Lie algebra of SUN into pieces according to this representation, then you get the 3 plus the 5 plus the odd representations. If you look at the SU infinity, so this is the way it works. If you look at SU infinity, so this is the C infinity functions on the 2-sphere modulo the constants. So these are the breaks up into the harmonics, spherical harmonics, which is the 3 plus the 5 plus the 7 all the way. So if you like, the Lie algebra of SUN does sit inside here. It's just that the bracket is not a Lie subalgebra. So there's a different bracket.
Other questions? So in the end, when you were writing down sort of this analogous of a harmonic map,
Yeah.
so the target space for G has non-positive curvature?
Well, it's one of these infinite dimensional spaces. It's not quite clear what kind of curvature you're looking at. I mean,
Like in the sense of like the space of Kähler metrics.
well, that's a better place to look. So I haven't actually made the connection of the harmonic map with the space of Kähler metrics picture. The most so in fact there is a Finsler metric on very analogous to this on the space of Lagrangian submanifold. I mean, there's the, what is it called, the Hofer metric. That has some, but then I think that's very badly behaved. So I don't know whether that has negative curvature in any sense. I'm not sure. Yes, I think that maybe if you follow the Donaldson line and we look at the variation of the Kähler form along the fibers. So this hypersymplectic structure is such, although it's signature 2-2, the fibers have a Kähler structure. I think the property of that relative to the symplectic structure is may well be maybe one you can attack that by using. I mean, I've tried to use Donaldson's work in the past, but somehow Picard's analysis was much more effective. But in fact, Donaldson wrote a paper for my 60th birthday, which had something very similar to this, but not folded in a similar context. But it doesn't work for me in any of these analytical questions.
Okay, well, if there are no further questions, then let's thank the The next talk is at 11:30, and there should be fresh coffee outside.